I think you, first of all, thank you that there's still some there. That's very good. I don't want to make it too long. I think you're all tired. I'm talking about subtractive and additive color mixing. So this is two opposite ways of how to combine or subtract a color. And first of all, what we need to know is what we are talking about. And the light that we have, so that we all love, is sunlight, definitely. So, but in different conditions, sunlight looks also different. So you see here some curves. So this is from a clouded sky to a half-clouded sky, so different things in between. And so scientifically, one needed to decide what is a standard. And then some people decided, so this colored area here, down there, this is what we set as a standard, so the black body curve. And out of that, only a part is visible light. So it's here in German. I couldn't find a better picture that is in English. So, and that means only out of that we are interested in this spectrum. So just to explain to you the curves that we will have a look later. So visible light means from really dark blue, from UV actually, what we cannot see, to really dark blue, to just heat. So the more it gets red, it gets more heat. So, and when we combine this, and we put this on top of each other, then you see here the wavelengths, so that you have an idea what this graph means by colors. Okay, now we put this together, so we put a white together by additive color mixing. So we are adding colors together, and how we do that technically looks like this. This is the module that we have in our T1 or DL7 or formerly in our DL4 lights. And we have a lens on the very front that combines, that mixes everything that comes from the back. And you see there are on three sides there are LEDs. And the strange thing is, how do we get something that is 90 degrees to the output of the front lens to the front? And the secret, it's nothing really new. This is already in all the projectors. You see we have a mirror. So let's say on the left side here, we have red LEDs, then we have a mirror that reflects the red color to the front. And on the other side, we have a blue mirror that reflects the blue colors to the front, and in the back we can have the green ones. That mirrors are dichroic color filters. Dichroic means two colors, dichroic. So one color is reflected and all the rest is then less passed through. So this, of course, as you can imagine, if you're a little bit familiar with physics, this is, of course, generating some losses. And also, the lens that we have in the front will generate losses. We have put this into a light, and that is the T1 now. That is our latest one. And if we look at the T1, now we're having here the T1 only on me. And the T1 has very intense colors. So we are looking here through all the native colors. So let's have a look. So we have the blue, we have a green in there, we have a lime, an amber, and a red. So when you put all of this together and balance it, so they all need different intensity. So next thing, then you are back to an 8,000 Kelvin, in this case high CRI lights, and we're just fading through the colors now, so not the colors, through the CTCs. And we are flexible with the CRI. That's something that's really new. So no light had that before, that you can have on a slider the color rendering index. So did we do that already? I don't know. so I didn't pay attention. So, okay, this is now the fading through the CTCs, and now we are at 2700, and that is the, done yet now? Difficult for me to see here. Yeah. 2700, and we are now with the CRI high and low? Okay, good. So, I have a red shirt on purpose today, because that makes it easier for you to look at it, to see the differences. The higher the CRI, the lower the output is. So if we have to balance all that colors, so to a very even output, then we are losing output. If we are lowering the CRI, we are winning output, it's brighter. And what we discovered is that a lower CRI doesn't mean worse light in every case. It depends on the costumes. If I would wear a blue shirt, it would look already completely different. It depends on the skin tones as well, and it depends on what you want to compare it to or what the other lights are in your rigging. So sometimes a value about 80 is better than a 95, what this light can do. Okay. Then the limitations with this is we are using here 550 watt, and we are generating 11,000 lumens. I have to say only. Well, with the next light, you will see that we can generate with the same power much more light. We have a complex design. You saw this already with the color mixing in the module, so we're having losses in there already. Lower efficiency is what is the outcome out of that, and a complex control. We try to simplify this as much as possible, because the light internally receives either CMY or RGB signals and then works with all the 5 colors in there, so that you don't have to bother with this, because it's sometimes really difficult to adjust 5 colors to have a certain color tone or a white tone or all this. All the tones, the color tones that we have, the CTCs that we are calling up, they are with a virtual CTO wheel here in there. Okay. Now let's talk about the subtractive color mixing. Now that's a different animal. And what we're talking about is the Esprit. So can you switch to that? Okay, that is the Esprit. That's our latest baby, the new toy. And now you've seen already the color temperature is different. Now coming also from a different position, but I think you already can see the difference. This is a white LED. It's a special white LED, because with the T1, we're at such a high level of the light quality that we wanted to keep up with this light quality as much as we can with the white LED. You saw already, now it is 650 watt electrical power that we're using, and we are much brighter. It is 27,000 lumen that we can achieve with a white LED. The LEDs look like this in there. So we have 73 individual 10 watt LEDs. They are really tiny. And, but if you look at that complete area, it is quite an area where the light is emitted. It's about this size. And we are putting this on a heatsink. That is what you see where it's mounted on. The heatsink can be mounted and disassembled very easily. It's 4 screws. It's 4 screws in the back of the head that hold the cover, and it's 2 wires either side. So this is how easy you can change the LED module. It looks from the back of the light, it looks like that. So now you can see it's pretty easy to get it out and to put a new one in. But many people then ask, why are you doing an exchangeable LED module? So it's an LED that will last forever. LEDs as well don't last forever. That's one thing. And we'll see that later in a picture, what happens. They get old over time, but we want to keep up the quality of the light. So the only possibility is if there is something after, let's say, not 500 hours like with discharge lamps, but after, let's say, 5,000 or 10,000 hours, if the quality has got worse, then we would exchange them. There is an NFC on the LED module itself up there. You see it's a near field communication chip that tells you this PCB has worked in light serial number so-and-so, let's say 5,302 hours. Then it was in the light serial number so-and-so for another 2,000 hours. So you always can track what it is, and the light itself knows how bright it is still. So if you want to match, for example, in a TV set where it's really important, the lights that are in the front, you would simply ask the lights, how bright are you? They tell you by a color code. And then you simply tell them, okay, let's say I have 10 lights that are 85%. I have one that is only 80%. One is not that important, so I match them all to the 85%. And then there are another 4 that are full. So, but those would then automatically adjust by just sending one command to the lights that they should all equalize. Okay, inside the color mixing, inside the optical system, we have a usual CMY system, so those 4 flags, so the CMY and the variable CTO. The special thing with the Esprit is this sits inside the optical elements that you need to unify all those 73 rays to one ray. So with every other manufacturer, this stuff sits in front of it. And that is the unique thing. The color mixing is so even, it is so good, and under every condition you have a color, not something on the outside and white on the inside. So that is, in very short, the unique thing with the color mixing in an Esprit. That's how the product looks. You have it up there. We have quite some here. So the advantages is high lumen output, good efficiency. And this is what we are running here, is the CMY system already, a CMY as we know it. So that's something that nobody needs to be explained. It works like the usual thing. We are running here through the color flex. And I'll continue talking while this is running. The disadvantage is limited colors. Of course, with 3 flags, you can only achieve a certain amount of colors that are in between those 3 colors. If you have 5 LEDs on the light, you have a larger room for colors. Red is not good. Like with the discharge lamp, the red is limited. You will see that later in my diagrams, and you will see it on me especially. And the LEDs change over time. They also change in the dimming, how they behave while dimming. So that is all downsides of it. It looks like this. This is simply 2 LED modules, and if you look at it, that is the typical white LED coverage. You have the blue peak, and then all the rest over there, so from the turquoise, that's very little, over the green to the red. This is generated by the phosphor coating that is on top of the blue LED. When it goes old, it might look like this. I switch back and forth a little. You see? And this is stuff you cannot do anything about it. It is like that, and the only thing that you can do is change the LEDs. So there's no electronics that could then prevent this. On the T1, we have a sensor in the head, and it auto-calibrates. So it will always be the same. It will be less bright after a time, but as long as you allow it from time to time to calibrate, it will always be the same quality. So the transferable engine is important, that we have the ability to maintain the quality about the complete inventory that you have in your stock. So if you buy a light in 5 years, for example, it might be that we have an LED in the meantime that gives us more output. We can change it. Very simple, 8 screws, 2 connectors. It might also be that the LED could then take more energy. We could feed more energy into it, but we need to be able to work with the energy as well, because the heat management system needs to be able to handle more energy. We have a 150 watt spare for handling the energy, so heat, in the heatsink, and we have another 150 watt in the basement in the power supply that we could call up for later developments. So whatever happens in the next 5 years, 6 years, 10 years, you are always up to date and you're absolutely at the forefront of the technology, and you don't need to buy a new light. So you just need to buy a LED source, and that is about the price of 2 standard discharge bulbs. So it's not too expensive. For those that have seen our PCB factory pictures that Joseph just presented further, earlier this afternoon, we do that PCB in our factory. That's why it's so cost effective. Told already that the data stays with the engine, with the near-field communication. As said, we have enough lifetime that we can extend to the future, and we can absolutely be sure that we are not losing on the next technology with the next generation of LED. So, let's talk about color temperature. We have not seen so many colors so far. Just for you, I think you're all professionals, these are the color temperatures. We can go from, let's say, 1,000 to 12,000 Kelvin. The 6,000 is, for us, is the reference. It is the sunlight with a little clouded sky. So this is how these curves look. That's, I think, nothing new to you. What you simply should remember is we have a peak in blue. If the color temperature is higher, we have no peak in blue when the color temperature is low, and we have a lot of red when the color temperature is low. Okay, now we're going to have a look at the T1 again. The T1 can do 8,000 Kelvin, and this is how we adjusted it now, on 8,000 Kelvin and full CRI, so maximum CRI. In the next picture, we have the same light, the T1, on 8,500 Kelvin. And now I've put there also the logo of the Esprit, and you can see the T1 has a orange frame, and the Esprit has a blue frame. This just indicates the color of the graph. So as long as it's an orange graph, it's about the T1. And when we're talking about we're talking about T1 now, right? And when we're talking about the Esprit, that is now, then it is the blue graph, and switch to the Esprit, please. And now I'm lit by the Esprit. And if you looked at that 2 waves, if you put them on top of each other, they are different, but they are rather similar. Okay, then the next color, that's the 5,600, the T1, please. Yeah, so. And we have the 5,600 with the Esprit. And let's have a look on top of this, these 2 graphs on top of each other, and you see already bigger differences. So now 4,200 Kelvin with the T1. We have programmed this just in between all the sessions. We had time to check it briefly, but we did not have any time to measure it correctly. So I hope it's all good. And I know that the further down we get to 2,700 Kelvin, the more you will see the differences. Might be not absolutely 100% correct what I'm telling you at the moment, because of the light might not be exactly the color temperature. Okay, then the Esprit, 4,200 Kelvin, different look already. And both of them on top of each other, the graphs already look quite different in the meantime. So 3,200 Kelvin, our beloved color temperature from the tungsten lights. And that's T1, of course, and now we're having the Esprit. 3200 Kelvin looks different, and if you look at the graphs, they look pretty much different already. So 2700 on the T1. Now it's getting really reddish. You know now why I'm wearing that red shirt, so that is really not only my special haircut, by the way, today, lots of skin. So also the red shirt, so that to be able to see the difference, and the esprit now 2700 Kelvin. So everything was to maximum CRI that we can get out of the lights, and everything was measured to the same brightness. So there's different color temperatures. Yeah, that's my little and quick as possible explanation about additive and subtractive color mixing, the advantages, disadvantages. When we look into the colors itself, that's another thing, but the purpose of this is to explain if we want to have a high quality white color, we need many colors, not just one white LED. So best quality of light output will always be an additive color mixing, and if you want real output, real power, then you will go for an esprit with a white engine. That's the comparison, forgot that, sorry. And let me say thank you.